Hi. So today we're looking at momentum. We're going to be able to define what momentum is, how you calculate it, and most importantly, we're going to define the principle of conservation of momentum. But as always, let's start off with some simple recall questions. Can you name 5 units for speed? What is Newton's first law? What is the equation for Newton's second law? And complete the following sentence for Newton's third law. If the Earth pulls me towards it, pause and answer those questions. I should have written Newton with a capital N. And let me fix that. Pen's not working. Whilst I do this, you answer the questions. Okay, pause, answer the questions. I'll try and get this pen working. Yeah, well, it's not working, which is pretty annoying, the whole lesson. So have you answered the questions? Good. Units for speed. We can have the most obvious one is, come on, pen, meters per second. Meters per second. Another one would be miles per hour. Another one, we could have kilometers per second. We could have centimeters per second. We could have millimeters per second. We could have kilometers per day. As long as we have a distance and then a time, we'll be fine. What is Newton's first law? Basically, in summary, come on, pen. This is a really shorthand. It's quite annoying. No force. No force. No change. That's not how you actually word it. I'm trying to write with the mouse, which is really tricky. No force, no change. If there is no resultant force upon an object, the object does not change. Basically, an object will carry on doing what it's doing if you leave it. What is the equation for Newton's second law? F equals ma is Newton's second law. And I'll complete the following sentence for Newton's third law. If the Earth pulls me towards it, I will then pull the Earth towards me. That's gravity. It's not like poetry or anything. That's just some gravitational attraction. Right, next page. So first of all, we're going to give you the equation for momentum, and then we'll explain what it means. The momentum of an object can be calculated using this equation. Momentum is equal to mass times velocity. Mass is obviously in kilos, velocity is meters per second, and momentum is measured in kilogram meters per second. Right, a lot of information there. Write it down. I'm going to change the battery in this pen, see if that works. Pause and answer the question. Right. Hopefully you fixed that. So let's move on to the next thing. So momentum, it's all about how far something moves and how big it is. And it's really about maybe how difficult it is to stop something. Here we have 2 instances. We have a large rhino and it's running towards us at probably quite a high speed. We have a squirrel running at probably quite a high speed too, because squirrels are quite fast, but a lot smaller than the rhino. Which one would you rather not be in charge of stopping? Well, which one? Which one, if I had to let you stand in front of one of them, which would it be? The rhinoceros, if you stood in the rhinoceros's way, it's probably a goodbye. The rhinoceros, one, moves very fast, but it's incredibly heavy. Whereas a squirrel is very, very light. The bigger an object is, the faster it moves, the more momentum it will have. So therefore, it will be more difficult to stop. You're not going to be able to stop a rhino, but you probably will be able to stop a squirrel. I'm not going to ask you to do this during the lesson. So let's just have a go. You're going to need a calculator. And to do this, I'll do some of these for you. And maybe you could just do one of them. So the first one, we have 0.5 mass times 25 meters per second speed. So that's nice and simple, which is 0.5 times 25, which is 12.5 kilograms meters per second. Let's try the golf ball one. 0.05 times 41. I need my calculator for that one. 0.05 times 41 equals 2.05 kilograms meters per second. Oh no, it's not kilograms. There's the line. And the tennis ball. Same mass, going a bit faster, times 63 meters per second. Let's do this one. It weighs about 1,000 kilos. It's going at 22 meters per second. 1,000 times 22,000 kilograms meters per second. So I ran out of space. I'm going to leave the last two for you to do. Okay? So, can you work out the momentum of the truck? And then work out the momentum of the white van. Pause and do those two questions. Okay? So, hopefully for this one, you got 130,000 kilograms meters per second. And this one was, oh no, that's wrong. 77,500 kilograms meters per second. So, although this truck was going less than half the speed of this white van, because this truck weighs a lot more, it has a lot more momentum. 130,000 compared to 77,000. Although this one is twice the speed, the mass of this one so much more, makes such a big difference in terms of what the momentum is. So for the momentum, you just take the mass in kilograms and you times it by the speed in meters per second. You may have noticed on these ones, it has the speed in miles per hour. Now, it's not always very handy. Actually, they gave you the speed in miles per hour and meters per second, but they don't always do that. So here's a way to convert it, and I might suggest you write that down. It's actually a lot simpler than it looks, but basically, if you want to convert from meters per second to miles per hour, you take the value in meters per second, and then you do the conversion. And so we want to convert meters per second into miles per hour. Well, first of all, there's 1,609 meters in a mile and 3,600 seconds in an hour. So you take the value in meters per second and times it by how many seconds there are in an hour. So say it was 13 meters per second times by that many seconds, because it's 13 meters per second times the seconds in an hour gives you the hour. And then if you divide it by 1069, which is how many meters in a mile, so 13 times 3,600 divided by 1609 gives us about 29.1 miles per hour. Okay? But every time you do it, you do this bit. 3,600 divided by 1,609. So actually, 3,600 divided by 1,609 is 2.22. So if we just do 13 times 2.23, that gives you 29 miles per hour. And so the shorthand way to do it is, if you want to convert meters per second to miles per hour, times it by 2.23. If you're doing the other way, and we want to work out what 30 miles an hour is in meters per second, well, it's just kind of like the same thing, but upside down. You times it by how many meters there are in a mile, and you divide it by the number of seconds, which is about 13.5 meters per second. And like I said, because you're always doing 1609 divided by 3600, you can just times it by 0.45 and all the answers are there. So it's really simple. Convert meters per second to miles per hour, times it by 2.23. Convert miles per hour to meters per second, times it by 0.45. Definitely worth noting down. Really handy. Here we go. Another example. We'll call this one A, B, C. Can you work those out? A, B, C. Pause, and I'll wait for you, okay? Have you done it? Splendid. Okay, so this one should have been 10 times 50, 500. This one was 12 times 10, which is 120. And this one is 70 times 13, which I can't do in my head. 70 times 13 is 910. And they're all kilogram meters per second. Check. Right. Now's a chance for you to do some of these real questions by yourself. I'll read them out to you, make it easier. For number one, it just wants you to work out the momentum in each of these cases. A, Jack has a mass of 50 kilos and he runs with a velocity of 8 meters per second. What's his momentum? A truck of mass 40,000 kilos is traveling at 18 meters per second, 40 miles an hour. What is its momentum? A car of mass 1,000 kilos is traveling at 31.6 meters per second. Well, what's its momentum? And a train of mass 120,000 kilos has a velocity of 40 meters per second. What's its momentum? Number two, you can get to work out the momentum of the Earth, which is always handy. The Earth has a mass of 6 times 10 to the 24 kilos. You know how to do that in standard form? My calculator is probably slightly different to yours, but I'm just do. You obviously press 6, and then you should have a button that says EXP. Press EXP, and mine it gives it as a little E, but yours might do it as the times 10, 24. So 6 EXP, there's a really annoying shadow reflection. 6 EXP 24 gives you that in mass, gives you the velocity of the Earth of 30,000 meters per second, about 67,000 miles per hour, pretty fast. What is its momentum? And the last one, ooh, tricky. The train had a momentum of 3,790,000 kilograms meters per second. If it had a mass of 120,000, what was its velocity? So we got momentum is mass. How have I drawn it so wrong? Sorry. Momentum is mass times velocity. You can work it out. Check. I'll give you the answers next lesson. Okay, scalar or vector. We know vectors. Velocity is a vector. What's the difference between a vector and a scalar? One has direction. So, if two objects of the same mass are moving in opposite directions but have the same speed, i.e. their velocities are, but they're at the same speed, i.e. their velocities are different, the momentum for each object will be the same magnitude but in a different direction. If two objects of the same mass are moving in opposite directions but at the same speed, so 30 miles an hour that way, 30 miles an hour that way. Speed, 30 miles an hour, doesn't matter. But velocity, 30 miles an hour that way, then that one would be minus 30 miles an hour. Different direction, different velocity. And because it's multiplied by a vector, it becomes a vector itself. So if we're talking about something going at a minus velocity, it just means it's going in the opposite direction to something that has a plus velocity. This, in a blue box, one of the most fundamental laws of all physics. Whenever two objects collide or interact, momentum is conserved. It's like the conservation of energy, but with momentum. If two objects collide or interact, the forces acting on each will be the same size but in opposite directions. The same is true for the change in momentum of each object. This means that the momentum lost by one of the objects will be gained by the other object. Whenever two objects collide or interact, momentum is conserved. And we look at this example at the start. We have two people standing there. I'm guessing it's on some ice because they're wearing ice skates and they're holding hands. Now, if we go back to Newton's third law, what happens if the girl just pushes? Newton's law says if object A puts a force on object B puts an equal and opposite force on object A. So if the girl pushes the boy pushes the girl. If she pushes the boy in that direction, the boy pushes back with an equal and opposite direction. So at the moment, when they're not moving, their momentum, because they've got V equals 0, their momentum is 0. But when they start moving, if one of them pushes, they both move. That's really important. If one pushes, it's not just going to be one moves, they both move to keep momentum conserved. How does this work? Handy. There's a little animation. So here they are. They're very much standing on ice, in love, practicing their dance routine. One of them pushes. Jack and Holly. Initially, no movement. Jack, heavier of the two, 60 kilos, he has a velocity of 0 meters per second, and so therefore a momentum of 0 kilograms meters per second. Holly, 40 kilos, also a velocity of 0 meters per second. Her momentum is also 0 kilograms per meters per second. But then they push. Beautiful. Holly moves away with a velocity of plus 3 meters per second. So, what's Holly's momentum? Quick maths lets you work out 3 times 40 is 120 kilograms meters per second. Now, for the rule of conservation of energy to be conserved, Jack's momentum has to be minus 120 kilograms meters per second. It has to be, because if you add 120 to minus 120, you get 0. Okay? And that's fine. That's good, because at the start they had 0, so they have to have 0 at the end. So his has to be minus 120. Well, you do a bit of rearranging. 120 divided by 60 gives you 2 meters per second. Momentum before equals momentum afterwards. Let's look at that again. So at the start, they have no momentum because they are not moving. 0 momentum because there is 0 movement. When they start moving, they're moving in opposite directions. So we look at their velocities, whatever. If Holly's is positive, Jack's has to be negative. So because they're moving apart, they're in opposite directions, so their direction is different, and velocity is a vector. So they one's positive, one's negative. Holly's momentum is the product of her mass times her velocity. So that gives us 120 kilograms meters per second. Jack's momentum has to be exactly negative. That has to be almost the opposite of that, because they had 0 before, they must have 0 afterwards. So we know his mass is 60. So 100 minus 120 divided by 60 gives us minus 2 meters per second. And that means before and after. 60 times minus 2 is 120. 40 times plus 3 is plus 120. Minus 120 plus 120 is 0. They started with 0. They finished with 0. Momentum is conserved. Now, we say that momentum is conserved in a collision. So we're talking about in that situation, there's two people, okay? But sometimes there are other things that momentum can get carried away by. They can get involved in collisions or interactions. So we can talk about collisions 2 types. We'll have an elastic collision or an inelastic collision. In an elastic collision, there's no energy lost or given out to the surroundings. All the energy stays within the object. So those two people, when they moved away, nothing else was involved. So all the energy was within them. their interaction was an elastic interaction. An inelastic collision, sometimes energy is lost to the surroundings in the form of heat. So if we just look at two objects that are having an inelastic collision, we might find that momentum wasn't conserved. But that doesn't mean the rule is broken. That means something else has happened that stole some of the momentum. Maybe a noise, some of the momentum went into sound in the air or transferred into something else. So the momentum is like in an inelastic collision, other things get involved and other things occur. So therefore, the momentum is not within those two things that it started with, or maybe three things. So elastic collision, no energy is given out to the surroundings. They were all within the objects. In inelastic, some energy is lost to the surroundings. Write that down. Pause, write it. Check. Okay, so let's have a look at this. So when things stick together, it's a good example of perhaps elastic type collisions, where we have a trolley of mass A and a trolley of mass B. They're coming together. So what's going to happen? So this has a mass of 3 kilos, and it's moving with 8 meters per second this direction. This has a the green one has a mass of 5 kilos, and it's going slower, but in that direction. If we work out their momentum, this one has a momentum of minus 20, and this one has a momentum of plus 24 kilograms meters per second. Okay, so the total momentum before is the sum of the two. So it's just 4 kilograms meters per second, plus 4. So after the collision, they still have to have plus 4 meters per second momentum, kilograms meters per second. Okay, when they stick together, they're now heavier. They have more mass. 3 kilograms plus 5 kilograms gives us 8 kilograms. And now we have everything we need. Momentum is 4. The mass is 8. So 8 divided by 4, 4 divided by 8 gives us a new speed of 0.5 meters per second, positive. So we can see, we can do it. Let's look at it. So that was 3, and that was 8, and that was 5, and that was minus 4. Boop, boop. So we've just worked out what happens with that scenario. If we launch it, we worked out that they stick together and they then move in the direction that the blue one is moving, in the positive way. Let's check it out. Oh, didn't move. That was rubbish. Should have carried on moving that direction. Shame on you. Fail. Okay, so now is a chance for you to practice some of those questions. It's a really simple equation. You just have to remember mass times velocity is momentum, and whatever the momentum is at the beginning, you have to have it at the end. So just make sure that happens. Question 4. Trolley A of mass 180 kilos, 180 grams, is moving with a velocity of 4 meters per second towards Trolley B, which is stationary and has a mass of 120. Trolley A then collides with B. Calculate the speed of Trolley B if the collision is elastic, Trolley A stops and Trolley B moves off, or the collision is inelastic, the two trolleys join together and move off. So you have two situations. Work out the momentum before, which is simple because one of them is not moving, and then the momentum after it has to be that, but there's two situations. One, the momentum after is where only one is moving, or the momentum after is where they are both moving. A squash ball of mass 24 grams moves towards a wall with a velocity of 16 meters per second. It strikes the wall, remaining in contact with the wall for 0.02 seconds before bouncing back with a speed of 12 meters per second. The initial momentum of the squash ball as it moves towards, we must calculate, the momentum as it's moving towards the wall. What's the momentum as it's moving away from the wall? And then the change in momentum. That's it. Been a lot of talking. Apologise. But there's 2 questions for you to do as well as other bits before. Good luck. I know you can do it. Love you. Bye.